Hello, everyone, and welcome to Understanding Physics, in which I will try to guide you through understanding what physics is. So, on General Physics 1, currently we have already talked about kinematics, but now we want to talk a little bit about mechanics. We want to talk about the force that causes an object to move. Well, basically, it is not that simple. So we could now just start trying to discuss what is actually force. So people might think that 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 force is a push or pull on the object, which is true. But here's the thing: back back in the days, people push. Sorry. People think that if you push an object, this will have a certain motion or a velocity. But with but with current understanding, this is this is not the case. Because if you have, for example, a block being pushed in ice, you only give it a light tap, this will still have some speed. So force is not the thing that causes an object to move, but instead force is something that changes the motion of the object. And this is what Galileo did, which basically redefines physics and 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 it basically describes almost everything that we have currently. So if you apply force, this will cause a change in the velocity, or basically this is the acceleration. So this is where Newton comes in, and he develops the three laws of motion. The first one is the law of inertia, which is basically stating that a body, uh, no, sorry, let's just write it like this: an object will stay at rest if no force is applied on it. Well, technically, it is more like an object will stay in motion if no force is applied to it. But here's a very big question as to what does it mean for something to stay in motion? What does that mean? Well, this is something to do with momentum. So basically what momentum is the m times the v. And if you don't apply any force to the object, this momentum will be the same. So i.e., you can say the dp over dt will be 0. So the second law states the same thing. An, an object will instead change its motion, i.e., if you state that the dp over dt is not 0, if force is applied on it. And so basically this states that if you have a force, this is basically the dp over dt. And this is what the definition of the force is. Lastly, we have the third law, which is the action-reaction. So, if an object, no, let's just write it like this. If A exerts a force on B, then B exerts a force on A with the same magnitude. And so this is basically the action reaction. And so this might not seem to be very familiar for you, the way that I write things, but we can state that the first law, basically the sum of F, would be 0, i.e. the momentum is 0, which is the definition of F. The second one, the sum of F, is the dp over dt. Well, we figured this out to be d over dt of mv. But since the m is constant, we could just state it as m of dv over dt, which is the thing that we call ma. And lastly, for the third one, we normally state that as the f vector from a to b is equal to the negative of the f vector from b to a. Okay, so let's just see certain examples of this. So let's say if you have a block and then somebody is pushing here about 50 newtons and somebody is pushing here about 50 newtons. Therefore, this guy will not move, or it might move, but at a constant velocity. But if somebody pushes, let's say 50 newton here, but then in here, let's say it's 60 newton, therefore there is a net force going this way, and this is where the acceleration comes in. And lastly, for the third law, sometimes people don't really get what the third law is truly stating. So let's just do it like this. If I have two blocks, and yeah, let's just say that this block A exerts a force on block B. That means that block B exerts a force on block A. And so if you look at this entire diagram, you would see that there is no force contributing from these guys. But if you actually check only one of these objects, you would see there is a force, which is the normal force. And this is one of the key components in a free body diagram, in which you separate things into each different objects which has their own different forces and analyze each of those forces. Okay, so that's quite interesting. So we want to also talk about what is inertia, because this first law is what people normally call as the law of inertia. So basically, inertia is how hard a thing needed to be pushed in order for it to move. And basically a measurement of inertia is basically mass. So if something has a high inertia, that means that it has a large mass. But if something has low inertia, it has low mass. So basically inertia is a qualitative description of a object. So we want to talk a little bit about something that we call as a inertial frame. And what is that? So basically what a inertial frame means is that you have a frame that is moving at a constant velocity. The v is constant for the reference frame. And this is where all of the laws will exist. But if you are dealing with a non-inertial frame, this is where the v of the reference is not a constant. That means that it has some acceleration. You would figure out that the first law fails to exist only because that you move something with a acceleration compared to something. So the way for you to actually view this is to actually talk about if you have sorry if you are in a car and then there is you there and then and then it is accelerating, you would feel yourself to feel a force going backwards, which is something quite weird if you actually try to think about it very hard. And so the way that we would actually describe this, okay, is that we could just actually model this into two blocks, first block and a second block, and this guy is given a force. Okay, that seems good. So if we want to try to draw the free body diagram, or only one of the components, we would see that for block A, or the car, we would see that it has a force going this way, and then there is also the weight going downwards. There's also a normal force going upwards, and don't forget there is something that you call friction, which is going in a certain direction. Let's say this direction. Okay. Yeah. Let's just say it is in that direction. So, what about this second block? Well, we know for a fact that it is moving in this direction relative to the ground, okay? So we would figure out that there's a force going in that direction, which is the friction, and then there's a normal force and there's also the weight. So here's the thing. Which of these are the action-reaction pair? Well, you might think that yeah, the weight and the normal force should be the action-reaction pair because they have the same magnitude and then they go in different directions. Well, that is not the case. In fact, the action-reaction pair for weight will later correspond to the Earth interacting with the object, and this is one of the key things that you need to always remember about. And so basically this normal pairs up with that one, and then this friction here comes from this friction as well. And so now we want to talk. Let's say if we only analyze the block and then we give it a reference point of this big block. Well, you see that it is you see that this block was accelerating to the right. But then if you actually check on this system, you would realize that there should be a frictional force going this way, which is the force of the frictional. And then there are some other forces such as the normal force. You still have the friction going in this direction, I think now. And yeah, there is still much more. So yeah, this guy should be normal, this guy should be weight. And so the question is, which one is the real force? The one that is pushing you forward, or the one that you feel when you move backwards? And this is one of the key components into actually trying to understand relativity, is that depending on your reference frame, you wouldn't know that if the force that you are hitting it is real or not. So that's one of the interesting topics that you could discuss in physics. So we have talked about these three laws of motion, and so now we want to talk about what are the forces that is available to us. So basically you would have four fundamental forces, which are gravity, the strong force, the weak force, and the electromagnetism force, or or yeah, the electromagnetic force. So this will later be discussed in electrodynamics, while this guy corresponds to why there exists a nucleus in a atom. While here it will discuss about why is there protons and neutrons, while gravity is the one that is keeping the universe together. And so physicists currently try to find a formula to write everything down in one single equation, which is called the theory of everything. And this is one of the research fields that we're still doing in physics, and this will later teach us a much more deeper understanding of the universe. So, anyways, we will later talk a little bit about gravity later in chapter 8, but for now we want to consider some simple cases of these four fundamental forces, which I will give three of them, or let's just say I will give four of them. So, the first one that we want to talk about is that everything has weight, and and this comes from gravity. Apart from that, every matter, when when it interacts with another matter, it won't fall straight through. Instead, this weight will later be countered by another force, which is the normal force. And basically the normal force is what separates matter. So basically what I'm saying is that if I have wood on the table, it won't fall through, thanks to the normal force. And so, what is the normal force? This is basically the EM force at a very tiny scale. Apart from that, let's say if I give this guy a force, well, this guy will exert some friction going in the other way. And this is what we call as the friction, and this also comes from the electromagnetic force interactions. And you can write friction to be a coefficient, multiply that by the normal force. And this will later be discussed much more fully in the next chapter. Another force that we want to discuss about is the tension force. So if you have an object, if you have an object and then there's another object, if you try to pull on this guy, there will be a tangent force that basically drags this guy around. And this is also a part of the electromagnetic force, in which that you have the atoms trying to cling on together. So, these are the forces that I want to emphasize a lot. And there is one certain force that I will try to discuss much more deeply, which is the tension as well as the weight. So, what is the weight of an object? So, the way that we will describe weight will be the mass multiplied that by the gravitational acceleration. And this seems to be very familiar to be the Newton's second law, and you can actually derive this from the Newton's law of gravity, and you will later get the weight to be the mass times the gravitational acceleration, which will equal to the mass times the acceleration. So therefore, any object in this world will later drop at the same acceleration. The other one is that we want to discuss a little bit about tension, but much more specifically in a spring, in a ideal spring. So let's say if you are a spring attached to a body, basically the tension force. So yeah, let's say that if you are a spring with a certain length, and then you pull this object to be a certain distance, let's say x, in this direction. This guy has a mass. This will later exert a force going backwards, which is the force to be equal to the minus kx. And so what does this minus sign actually resemble? So basically the minus sign resembles that it is going in the opposite direction of the way that we want. So basically this is like a restoring force. It is like no, you don't. I don't want you to go there, so my force will be opposing the direction in which you want to go. And so if you try to stretch the spring further and further, it will later become much more harder for you to pull, because your x is getting larger, therefore the force will also need to be larger. But this does not always work in true materials. So we have talked about every chapter that we need to discuss, and so now before we go, there is one example that I want to discuss a little bit more, which is the equilibrium point for a spring. And so this is a very easy thing for us to discuss together quickly. So we have a spring as well as an object with a certain mass, and there's gravitational acceleration going down. Okay, and let's just take the initial place of the object to be at x equals to 0 before we drop it. So there is no force from the spring. So the F spring will be still 0. So here's the question. If I let it go, and then I will wait for a while until it will later stop moving, at what length will it be? So this will be a very interesting question for us to discuss. So let's just first try to define our coordinate system. And let's just state the one going down will be positive x. And so, if we actually try to check this out, we would have an object here. So yeah, this will be the free body diagram for the mass. This will have a tension force, or sometimes I call it the F of spring. And then later going down, there should be weight. And then I define the axis to go down. This is x positive. So the way that I will solve this is that I will actually first try to check every single force. So I will first check this weight first. The weight is mg going downwards, but then you subtract it by the negative k of x going upwards. It is going in the opposite direction. Well, technically it is not the negative kx, instead it is kx. So you really need to be careful about the sign that you use. But the easiest way for you to think about this is that you need to remember about the direction, and so this will only discuss about the magnitude. And so if you check this to be negative, the force of the spring should later be positive. Should be positive in total, which it is the case. And so this case, I hope this to be zero, in which it is at its equilibrium point, in which its acceleration to be zero. You would later figure out that the x will be the, whoops, it is the mg over k. And so what's k? So k's unit is newtons per meter, where unit is the unit for force, or you could write it as the kilogram meter per second squared. And so if you try to check the unit, you would have the kilogram per meter. Okay, so the mg, that's Newton, divided by Newton over meter, which will later be meter. And so this is the position in which you will find the object. And so if you increase the mass, or you increase the gravitational acceleration, it will later be much more sloppy. Sorry, it is like much more further compared if you do it in a normal case. And then if you try to strengthen the spring, it will later try to retract it. Therefore, it will be on its negative direction. No, sorry. It will be in a much more smaller value. So the way that we'll actually see this is from the simulation that I have set up here. This doesn't look to be that similar, but if you actually see this red line, which resembles the force, you would see that it will later equal to 0 at this point of mg over k. And so if you try to increase the strength of the spring, you can see that it goes much more nearer to 0. The same thing if you actually reduce the gravitational acceleration, or if you try to increase the mass of the object. And so this is one of the key things that you need to realize in doing physics, is that you want to make sure that your result makes sense. So that's all for today, and I hope that this teaching will later be applicable in your daily life. So thank you very much, and I will see you guys on the next chapter.